Welcome to our webinar on argument-driven engineering. The program has been under development for several years and was researched at the University of Texas and piloted in multiple classrooms. So argument-driven engineering is an instructional model that's designed to help students learn the core ideas of both science, math, and engineering by doing STEM design challenges. So our hope is to get students involved in solving real-world problems here. And we've got an amazing facilitator tonight to help introduce that. So I'll introduce myself first. My name's Carrie Burt. I'm a professional learning specialist with Argument-Driven Inquiry, and our facilitator is going to be Jen Kashuba. She's our professional learning coordinator. Jen is one of the authors on our upcoming 5th grade book, and she's very knowledgeable and passionate about improving outcomes for students in all grade levels. So Jen, I'll go ahead and turn it over to you.
Thanks, Carrie. So as Carrie said, ADE is a way to help students use the core ideas of both science, engineering, and mathematics to help make the world a better place. And so one of the things that we want to start with is just a common definition of STEM. So we see this as a way to encourage the use of those ideas, incorporate technology, and to get kids engaged in all 4 of these areas at the same time. So some of the mathematical practices we target and the science and engineering practices as listed in the NGSS are there on the screen for you. And these are really what we think about as we're building a design challenge. So we start with a real world issue, not to say that kids don't live in a real world, but not a contrived, made up issue. It's something that actually is faced by people who work in these fields every day, or that if kids come up with a solution to it, it's not something that's just going to get a poster on the wall, but something that may actually help them change the world or see how they can change the world, because that's really engaging to a lot of students. And so we designed out design challenges that have 3 things in common. They are purposeful, so we give them a goal, we help them understand the goal. They're constrained, so just like engineers, the students will be faced with both criteria and constraints. It's not just design something to save the world. We give them specific things that might have come in from a client or that are practical issues that they might have to deal with. For example, in the one we're going to talk about tonight, they're designing a container to help keep vaccines at a certain temperature. And as you can imagine, since vaccines, the reason they had this design challenge, we'll come back to that, was they really wanted to get vaccines into areas of 3rd world countries that didn't traditionally have access to them because of lack of electricity to keep them refrigerated. And so you can't just ship a huge container overseas. So they had to fit within a certain space limit. So those are things that might play into the criteria and constraints. And the other thing about the design challenge is, just as engineers that are designing things do, we keep it systematic and iterative. So they have to make mistakes. You have to give them time to make mistakes, and they refine their product, so to speak, and their process over time. And these things, I guess, goals of a design challenge come out of the STEM integration in K-12 education research that's part of the National Academy of Engineering and National Research Council's literature. So here are the stages to argument-driven engineering. And if you're familiar with argument-driven inquiry, we still have 8 stages here, similar in layout. But in this case, we have a lot more things that happen in each stage. So what you see here is what the students are going to be doing. So for example, stage 1, you provide a design challenge to them. They identify the criteria and constraints. And from that, they produce a document that has their design parameters. Stage 2 is concept generation, and so on. And so we're going to talk through each of these stages this evening, just to give you an overview of what ADE can do for you and your students. So stage 1 is to introduce the problem. So we give them a meaningful problem to solve. For example, one of the Gates Foundation challenges was to find a way to keep vaccines cold when you deliver them to places like 3rd world countries in the middle of Africa, or sub-Saharan places, the middle of the rainforest, India, for example, those kinds of places. And so we give them the meaningful problem. We give them core ideas that will help them. So this is the science content that's going to help them. In this case, they're using the idea of thermal energy and how thermal energy moves, what does it mean to be an insulator, what does it mean to be a conductor, those kinds of things. And then we give them a design challenge based on a performance expectation from the NGSS. So all of our design challenges are aligned to the NGSS, and they encourage the students, as I said, to help make the world a better place. So they see that not only are we engaging in engineering, but we're doing it for a purpose. So students go through and determine what their criteria and the constraints are. So you see an example of that here, where they've been introduced to the problem and they've decided this is what we have to do, this is what we should do, this is what we are going to get a better score on. So this is why a client might choose our product, or why the Gates Foundation might have privileged one design over another. From that, they do concept generation. So they think of potential designs that they could create. Usually we do this as individual students so that every student gets a chance to come up with several designs. And then they work through concept selection. So they actually create an evaluation matrix or a decision matrix, and they have to use the criterion constraints and rate of each of their concepts within their small group. So they put all the ideas on the table. At this point, they can choose to keep parts of different designs. That's up to the students. And then they go into the design argumentation phase. So before they ever build a prototype, they have to state to the group why they think a certain design should go to prototype, because prototyping takes a lot of time and it takes resources. And so engineers don't just build prototypes every day. They have to propose that something go to prototyping. So the students here have made a claim that this design is the one that they think that will work best. And you see they've done a wonderful three-dimensional drawing of that. And then they've outlined their reasons. This is why they think this is the best design. And so that's where they get into how this meets the criteria, the constraints. And you'll also see that students will begin to incorporate the scientific ideas. More of that will come up later as they finalize their designs. You'll see that then they have to justify why that design is best based on the science itself. So these students are engaged in an argumentation session where they are convincing classmates from another group why this is the best, and those classmates are pushing back at them and asking them questions about how that design is going to work, pointing out potential flaws in it. So very much a collaborative atmosphere where they are trying to help each other really come up with the best design. So here's what that argumentation board would look like. So they have the question, their claim, which is the picture of their prototype, the underlying science, how much it costs, how it meets the criteria, and then the reasoning further goes into why they should choose that one based on the evaluation criteria. From there, we go into a set of steps that is very systematic and iterative for testing and refinement. And this is not just a one-day thing. Students should be given multiple chances to build their prototype, test it, determine whether or not, for example, this one keeps that temperature that they are aiming for, which does take 24 hours. So they have to allow it to sit overnight, and then they come back the next day and they determine if the design has met the criteria. And then they will rebuild a new version of it and again test it. And so this is something that you don't want to drag it out too much, but what engineers do. They don't expect perfection, and they're constantly refining, redesigning, just tweaking things just a little bit. The next step is to actually take that final product and go through an evaluation argumentation. So this is a little bit more detailed than what we saw with the prototype argumentation, but here they are going in and looking at, this is why our device is the best, okay? And this group actually said it wasn't successful, which is kind of funny for students to realize that it met every other criteria, but it didn't keep the vaccine as cold as it should have. And so it becomes an issue of, is that then a success because it meets 95% of the criteria, but it didn't meet probably the most important one? And they have some great conversations about that. They also look at how they really failed to meet that and why the science might not have been in their favor, because they start talking about thermal energy transfer and why they weren't able to keep it cold. And so they start to realize, really, why does temperature change? Why does, energy go from hot to cold? In fact, one of my favorite kind of things that came out of the research is on one of the students' handouts. There's a little line, and it has where he's annotated, and he talks about the fact that it can't go from cold to hot. And he's like, of course, because you can't, a cold thing that's moving slow can't make things move faster. So it has to be the faster moving molecules that are speeding up the slower ones. And it was this just beautiful explanation from the standpoint of a middle school student about thermal energy transfer and why they needed more insulation material, because the fast moving molecules on the outside they were going to hit the thing. He admits that, but it was going to do layer after layer. And so the more layers of insulation, or the more rigid the insulation. And what he was really looking at is kind of the R value of things without really knowing about it from a true, engineering builder's perspective. But it was just a very elegant explanation. And so you see that come out in their evaluation argumentation. And they have another argumentation session to really talk about, what is your evidence? What are the flaws in your design again? What is your justification? What are the flaws in your justification? What have you forgotten to incorporate? Oops, sorry. So this is what those boards look like. So they have their question and they make their claim this time. And then they have their analyzed data with an interpretation of the analysis. So what does it really mean? Why that evidence matters? And then they have to include information about the design parameters. So here's another example of one of those boards. So in this case, they've chosen to present their evidence as a table of the requirements, the performance, the target, and whether or not it met the target. And here you see their design was a little box that had a lid that came down and kept the vials, which is just some colored alcohol. By the way, we don't obviously give them real vaccines, but the kids, some of them think it is, and they're scared to even touch it. But it's a little vial of colored alcohol. And so they've designed that. It doesn't have the ice packs, I believe, that were included in this one. Okay, so this one actually met all of the criteria and did manage to keep it cold, and was, under the cost. It was as lightweight as possible and all those other things. The next stage, stage 7, is very similar to stage 5. If you're familiar with ADI, we have a reflective and really discuss what happened. So we give them time to be metacognitive. We give them time to reflect on their own procedure, their own way of doing things. What do they think? What do they know about the science? How did they use the science? What would they do differently? What were the kind of drawbacks to the way they approached certain things? But really reflect on the science and the process. And so think about the science and engineering practices that they've gone through. Think about cross-cutting concepts. Think about the way they analyzed it from a mathematical perspective. If technology has been part of their design, how did they use technology, and what did it afford them? What did it add in terms of a constraint? All of those kinds of things play into this reflective discussion. And obviously all along you've been having kind of mini discussions, but this one is a little bit more intentional to make sure that you've cleared up misconceptions that they might have about any of these things. You give them a chance to discuss and clarify questions amongst each other. It is not meant to be a lecture. It is meant to be them discussing amongst themselves. Stage 8 is the report development. And so this is a small piece of what they do in their report, but they do prepare a design report. So they have to discuss, what are you trying to solve? What was your design process? How well did you do it? And then again, that science behind it. So while we are doing engineering, it is very focused, as the NGSS is, on performance expectations that incorporate science concepts. And so we have 4 different design challenges that will be out hopefully next year for middle school, that are available if you attend professional development or you bring us in for professional development. There's vaccines. There's a crash safety test barrier one. We have another one on keeping people's hands warm, and predominantly designed for people who might be experiencing homelessness. So that one has to do with chemical reactions. And the last has to do with ecology and testing for bugs in a certain area to judge the health of the ecosystem. And so they are trying to design a way to catch these little bugs while not catching other organisms that you don't want to harm as you try to collect your data. So they write the report, and then we go through a peer review of the reports. So they actually do a double-blind peer review. So students are reviewing each other's reports in a small group. And this helps them to, again, discuss evidence, see if the evidence backs up the claim of that group. Did they really meet the constraints and criteria of this? Did they incorporate the science into their justification piece? You know, if they have a graph, is it presented properly? So students are giving each other feedback on this, much in the same way that scientific researchers or any researchers actually do a poster session. That's our argumentation piece. This is very similar to how you would do a peer review of an article that you're trying to get published. But obviously these are a little bit rougher than articles that are ready to be published. So maybe you send it out to a friend before you submit it for publication, but that's what we're getting them ready to do, is to give and receive feedback. And so you'll see here the author also decides which of these revisions to make in their report and why. So they also get that learning how to accept feedback piece. And then the last part of that stage is to submit the final report. So if you want to learn more about argument-driven engineering, our website is www.argumentdriveninquiry.com. We also have professional learning opportunities. Currently, ADE is offered as a district-based, or if you have a group of districts in an area that want to pool their resources to bring us in. We've had a couple of face-to-face workshops, but we don't have any planned at this time for registration-based, but we're willing to come out and do this with a district. Most often, I'll say in the face-to-face workshops, we do our crash safety test barrier. The vaccine one with a 24-hour testing time obviously takes a little bit long, but that also gets you access to the pre-publication versions of the design challenges. We also offer a very unique opportunity, and this is limited in number of how many we will support each summer, but we have an ADE STEM camp, which incorporates both professional development for your teachers along with face-to-face interaction with your students. So what we do is we come in and we train your teachers for a couple days, and then our team members work alongside your teachers to deliver the STEM camp directly to students to help build that capacity within your teachers so they are very familiar with the model and they feel comfortable implementing it and then can take it into their classrooms or do a STEM camp of their own the following year. So again, if you have any questions, feel free to email us. I'm also going to pause and reflect on a couple things while anybody who has any questions types them into the Q&A. So some of the important things to think about as you start using ADE is to keep an open mind. So if you think something might be too challenging or difficult for some of your students, don't dismiss it. This is an example of a crash safety test barrier. So you see the little cart is the blue that came down a ramp and crashed into their barrier. And then on the right-hand side, you can barely see the force probe. But this particular group of students this is one of the best designs we've ever seen. This is better than most of the engineers who helped design these things could come up with. And this particular group of students was a struggling group of students in one of our STEM camps who had traditionally underperformed in science classes. And they excelled at this. They knew the science behind it because they sat and discussed it so much. They tested, they did that iterative process, and they came up with a very, very elegant design, but they understood that what they were trying to do was reduce the force, and they did it largely through the friction of that middle pad on the popsicle sticks. And it's just so elegant. But for years, these students had been told that they really weren't good at science, and here they came and had one of the best designs possible because they truly were given a chance to use the science in a meaningful way. And so they started thinking about it more than if they were doing something that might be more traditional classroom activity. The other thing we want you to think about is access. So how can you give all of your students equal access to this type of learning experience? So if you're doing a STEM camp, for example, how do you ensure that you have a demographic representation of your entire school or your entire district, that it's not all a certain gender or a certain socioeconomic status represented. And so one of the things that we like to focus on with ADE is actually taking it into the science classrooms. For those of you who teach the NGSS, it is highly likely that you have a engineering performance expectation at your grade level. And so this helps you address that performance expectation, but also gives all the students access, because if you do this across all of your classes, for example, in 8th grade science, then all students would have access to it. We did not mean for ADE to just be an after-school experience. And so the team that developed it really focused on ADE for everyone as a way to ensure equity. And that also goes to, how do we make sure that all students feel their participation and ideas are valued? That's one of the reasons, for example, that the brainstorming of initial ideas is an individual piece, and then all students present to their small group, rather than, okay, guys, start working on it and one student dominates that. So how do you make sure that everyone has access to participate? And so those are kind of our three main tenets of using it or thinking about it, is that we don't want it to be just an after-school pullout that appeals to a certain gender or a certain race. And so how do we make it inclusive for everybody? So I see a couple questions.
All right. So the first question that we have is, we actually have two from Tony, and he's asking, first, how many challenges are included in this volume? And then when will the books be published?
Okay. That's a great question. So there are currently 4 design challenges because there are 4 performance expectations in the middle school NGSS that require design challenges, and so that's what they were written for. We anticipate the book to be probably out next spring, I think. That largely depends on the publishing timeline and how many edits are requested, and these books, similar to anything that gets published, go through reviewers, and so our hope is that they will be out by next spring. But again, you can get pre-publication materials if you are fortunate enough to have us out for a workshop.
All right. Next question is, what content courses could this be a part of? Could this be a standalone engineering course or incorporated into a content course?
That's a good question. Yeah, we've designed these to be used predominantly in science classrooms, but if you have a standalone engineering class, these would definitely help to build up that curriculum. They take about 2 to 3 weeks each if you have a 55-minute class period. So I don't know that the 4 challenges in and of themselves would be a complete curriculum for an engineering class, but they are definitely a great supplement for such a class, or it could be what you build the rest of your course around.
All right. Another question is, what advice do you have if I want to write my own ADEs?
Okay, so no, that's a great question about how to design your own ADE. So first of all, I would think about what application you want to address. So what is the challenge that you want to give them? And how does it relate to the content that you're required to teach? So those two things sort of have to be done in tandem. And so what is your content? What is a out of school, not made up situation? So we're not, pretending to build a life chamber for an alien that shows up. Maybe that's a real world situation later on in life that we might see that, but right now it's not. So instead, like maybe how do we build a way for humans to go to Mars? That's something that people in the field are actually facing, is how do you build a life support system to send somebody to another planet? So that's more of a realistic situation, I guess, because that's what we want to focus on. Is kids are quick to realize when something is contrived, and it's not a practical application in any way, shape, or form. So I would start with that. And then you can kind of think through the stages. You would have to create all the background information documents. You have to think about what materials you're going to allow them to use, and structure how much does each material cost. How much space am I going to give them to have this thing? If they're building a scale model, what does that mean? And that'll help you back up and develop the criteria and the constraints, which you also have to think out. And then you have to have a way of them testing it. So for vaccines, it's keeping this vial cold. For the crash safety barrier, it's actually crashing a cart of a certain mass into your barrier, and it has to have a certain performance. And so those kinds of things you have to think about, because that's what's going to build you your criteria and constraints and how you're going to test it. So it can take a long time to write one of these. It's not, completely outside the realm of possibility for folks, but it does take a little forethought.
All right, we have one last question. So Matt asked, we know that ADI covers a lot of ELA and science standards, and ADE seems to do that as well. Do the challenges align with any other content standards, such as math or social studies?
So the challenges themselves have not been aligned to social studies. I think you could incorporate certain aspects of that into, especially like the vaccine one, because you are talking about taking them into an area where politics plays a part in this delivery also. Or if you're working on geography, what does that mean in terms of, transporting these things? They are aligned to math because the students are going to be collecting data, they're going to be graphing, they're going to be looking for patterns in a very similar way. The crash safety test barrier can be done with or without students actually having to do the calculations of how much they've reduced the force. Because you can either use a force probe, which does it for you directly, or you can actually calculate, you can have a probe that does the acceleration of the cart and how fast it decelerates. And then from that, they can back up and calculate the force. So you can add in additional math if that's your goal, or you can simplify the math to it, being kind of more data analysis versus algebra based, depending on the level of your students and what grades you want to use this with.
All right, that's it for us tonight. Thank you again, everyone, for coming and hanging out with us and learning a little more about argument-driven engineering. If you have other questions, we would love to answer them. You can email Jen at jen@argumentdriveninquiry.com. You can check us out on our website, and join us for Facebook or Twitter, or any of those. So we'd love to hear more from you. And yeah, have a great night.